Welcome to Starship TV. The planet Mercury, an in-depth exploration of the innermost planet of the solar system.
Mercury, the closest planet to the Sun, is a small, rocky world of extremes. Despite its proximity to Earth, it remains relatively enigmatic compared to its planetary neighbors. This report explores the known characteristics of Mercury, delves into its unusual properties, highlights obscure facts, and assesses its exploration history and potential for future human interaction.
General characteristics. Diameter, 4,879 kilometers, 3,032 miles.
Distance from the Sun, approximately 57.9 million kilometers, 36 million miles.
Orbital period, 88 Earth days. Rotation period, 58.6 Earth days.
Atmosphere, extremely thin exosphere composed mainly of oxygen, sodium, hydrogen, helium, and potassium. Surface temperature range, daytime maximum, 427 degrees Celsius equals 800.6 degrees Fahrenheit.
Nighttime minimum, minus 173 degrees Celsius equals minus 279.4 degrees Fahrenheit. Gravity, 3.7 meters per square second, about 38% of Earth's gravity. Magnetic field.
Present, but about 1% the strength of Earth's.
Relationship with the Sun. Mercury's proximity to the Sun dominates its environmental conditions. Tidal locking, 3:2 resonance. Mercury is not tidally locked in the same way the Moon is to Earth.
Instead, it is in a 3:2 spin orbit resonance, meaning it rotates 3 times on its axis for every 2 orbits around the Sun. This results in a Mercury day lasting 176 Earth days. Solar intensity receives about 6.5 times more solar energy per square meter than Earth.
Perihelion precession. Mercury's orbit is elliptical, and its perihelion, closest approach to the Sun, advances over time.
This anomaly was a puzzle that was famously explained by Einstein's general theory of relativity, marking a pivotal moment in physics.
Oddities and obscure facts.
1. Ice in shadowed craters.
Despite searing daytime temperatures, radar observations and data from NASA's Messenger spacecraft have confirmed the presence of water ice in permanently shadowed craters at Mercury's poles.
These regions never see sunlight, creating cold traps.
2. Surface composition mysteries.
Mercury has an unusually high metal-to-silicate ratio compared to other terrestrial planets.
Theories to explain this include: early solar blow-off of lighter elements.
A massive ancient collision stripping away much of the mantle.
3. Hollows, a unique geological feature. Mercury hosts mysterious hollows, irregular, shallow depressions with bright interiors.
These are thought to be formed by volatile substances sublimating into space, but the exact mechanism is still not fully understood.
4. Magnetosphere oddities.
Mercury has a magnetic field, despite its small size and slow rotation, which defies earlier expectations.
It suggests a partially molten, iron-rich core generating a dynamo effect. 5. Tails like a comet.
Mercury has a comet-like tail made of sodium atoms, stretched out by solar radiation pressure and the solar wind.
This is visible in ultraviolet observations. 6. Unusual colors.
While Mercury appears gray and dull in visible light, enhanced color images reveal subtle shades of blue, brown, and orange, indicating different rock compositions.
Exploration history. Past missions.
Mariner 10, 1974-1975, first spacecraft to visit Mercury, mapping about 45% of its surface. Messenger, 2011-2015, orbited Mercury, providing detailed maps, elemental composition data, and evidence of ice deposits.
Current missions.
Habitable, launched 2018, arrival 2025, a joint ESA-JAXA mission currently en route, carrying 2 orbiters designed to investigate Mercury's magnetic field, magnetosphere, and surface composition.
Planned/future missions. As of now, no human missions to Mercury are planned due to its harsh conditions, but robotic exploration may continue beyond Habitable. Potential for exploration and habitation. Exploration feasibility.
Robotic exploration, favorable for studying planetary formation, exosphere chemistry, and solar interactions.
Mercury's surface is relatively accessible for landers, though extreme temperatures pose technical challenges. Scientific value, high for planetary scientists, particularly in understanding early solar system history and comparing planetary cores. Habitation potential. Technological barriers, the extreme heat during the Mercurian day and freezing cold at night make habitation highly impractical. Polar regions, the poles, particularly areas with permanent shadows, offer the most stable environments and potential resources, like water ice. Energy potential, solar energy is abundant, though infrastructure would need to withstand intense heat and radiation. Psychological and health hazards, constant exposure to intense solar radiation and extreme temperatures would require heavily shielded habitats, making Mercury a highly hostile environment for humans. Conclusion on habitation. Mercury is among the least hospitable planets for human settlement. Any near-term human presence would be limited to brief robotic or remote-controlled scientific outposts. Conclusion. Mercury is a planet of paradoxes, a scorched world that harbors ice, a tiny planet with a robust metal core, and a seemingly dead world with active surface processes. While its proximity to the Sun makes human visitation difficult, Mercury offers a unique laboratory for understanding the dynamics of rocky planets, the effects of intense solar radiation, and the mysteries of planetary evolution. Is there a more temperate zone on Mercury? Mercury's surface temperature extremes are some of the harshest in the solar system. There are, however, regions that are slightly more moderate compared to the searing equator or the freezing night side. 1. Twilight Belt, Terminator Zone. Definition: the terminator is the dividing line between the day side and night side. Temperature stability: along this zone, temperatures may remain within a more stable range, though stable on Mercury still means extremes. Estimated temperatures. In these areas during sunrise or sunset phases, temperatures might range from -100 degrees Celsius to 100 degrees Celsius, a relative moderation compared to the blistering 427 degrees Celsius at the subsolar point, noon at the equator. Challenges. The terminator is constantly moving due to the planet's slow rotation. This would make establishing a permanent base challenging unless it could chase the terminator, which would require continuous movement. Potential for solar shielding. The fact that the Sun hangs low in the sky along the terminator would make solar shielding more manageable compared to the subsolar point. 2. Polar regions, better prospects. Reason for interest: permanently shadowed craters near the poles offer the most stable cold environments, with temperatures consistently around -170 degrees Celsius, preventing extreme daily swings. Potential for use. Could provide natural protection from the sun. Known ice deposits could serve as a water resource, essential for life support systems. However, these regions are always dark, requiring artificial light and power. 3. Subterminator regions. Some planetary scientists propose the subterminator zones, zones slightly inside the night side near the terminator, might provide the most theoretically stable locations for temporary human outposts. These regions could offer protection from direct solar radiation, reduced risk from the extreme thermal cycling of the dayside, temperatures still cold, but less extreme than the deep night side. Most habitable zones, in degree F. Region daytime temp max nighttime temp min notes. Equatorial dayside 801 degrees Fahrenheit -280 degrees Fahrenheit most extreme swings, not viable. Twilight/terminator zone 212 degree F-148 degree F slightly more moderate, but moves constantly. Polar craters always -274 degree F always -274 degree F constant cold, ice deposits, stable zone. Subterminator regions less than 32 degrees Fahrenheit -238 degree F best compromise, but still harsh. Conclusion on habitability zones. No place on Mercury is naturally habitable. Subterminator regions and polar craters offer the most practical options for robotic or highly shielded human outposts. Technological solutions would need to account for extreme temperature gradients, solar radiation, and absence of atmosphere.